Welcome to Programming in Modern C++. We are in week 10 and we are going to discuss module 48. In the last module, we have continued on introducing some general features of C++ 11. We have talked about initializer list, the braced initialization and its consequences, and also the uniform initialization mechanism, which can be uniformly used everywhere in C++ 11. And we have also seen a convenience mechanism for iteration over an entire data structure by using the range for statement. We will continue on these and introduce several of other general features of C++ 11, which are on one side for convenience, for safety, for efficiency, and as well as will become important for the later important features. So, these are the 6 features that we are going to talk about in this module. This will be our outline naturally, which will be available on the left. So, let us start with const expression. Const expression is a feature to evaluate constant expressions at compile time. So, let us see what it means. Is const expression is in a way more, it gives us more than the general constant expressions. We have constant expression or const seen earlier. It will provide for somewhat more and with some differences. It allows constant expressions involving user defined types and provide a way to guarantee that an initialization is done at compile time for a const expression, given that you have the constants available at compile time. So, here is a simple example of an enum of flags having 4 different possible enumerable values, and we are defining an operator OR for 2 flags f1 and f2. Now, if you look at this, then this is it basically takes the flag f1 and the flag f2, converts each to int. As you know, normal enum can be converted to int, and then returns the value as an int value, right. So, that is what the flags are doing. Now, what will you have? Since if you know the values of the flags f1 and f2 at the time of compilation, naturally this entire expression can be evaluated at the compile time. So, as an illustration of that, let us see, we have a flag, we have a switch based on this flag type x. Now, as you know, the cases of the switch need to be constants at the compile time. So, it is quite obvious that I can have case bad, which is basically case 2, I can have case UF, which is case 4, but I wanted to write case bad or UF. This is an operation which normally you will expect at the runtime. But if that happens at the runtime, then this code cannot compile. This code will not compile because you will not know what is the value of bad or UF as a constant at the compile time, and switch case will not allow that. So, without this const expression, this code will not compile. But what will happen with the const expression? With the const expression at the compile time, f1 will be treated as bad, UF will be treated as f2 will be treated as UF, and it will actually compute the OR of these two, and whatever is that ORed value. So, if I have 0 0 1 0 and UF is 4. So, if I have OR of that, so for this value, this case will be applicable, right. So, this is possible because we can evaluate this expression at the constant as a constant expression at the compile time. So, this is the basic feature of the const expression as we have. So, typically the const expression is a function that must be of simple form, that it can be evaluated at compile time given the constant expression, and it is not only that it gives us an ability to evaluate expressions at compile time, but we want to be able to require expressions to be evaluated at compile time, because that gives better efficiency and of the code that we have. So, const expression in the form in front of a variable definition will does that and will do that, and will also mean what we traditionally mean by const. So, this is a different context. So, we have const expression before int x, and this is an expression which can be evaluated at compile time. So, it will evaluate, have a constant value, and will treat this as a constant. Similarly, but if we try to do, say in flags, in this function, if we try to do this, see f3 is a parameter and I am using that. Now, this function will get the value of f3 at the runtime, and only then it will know what is bad or f3, right. So, you cannot evaluate this as a const expression, but if you just do bad or f3, you will be able to do that. In fact, if you do const int x3 bad or f3, that will also be valid, because const does not need the evaluation to happen at the compile time. It only says that it has to be a constant expression. We have already seen the use of const expression in module 47 in the standard library initializer list. So, it can be used, const expression can be used with user defined types also. Here is an example. We have a struct point, and I have specified the constructor to be const expression. So, const expression point origin 0 0 will actually at the compile time construct this object and will also set the values of x and y. Similarly, it can then set z as a const expression origo dot x, which will actually get 0, and so on so forth, the arrays and so on. So, all of these different types of const expressions are possible. Note the difference between const and const expression. It is not, in general, one is not a replacement of the other. Const's primary concern is to express the idea that the object is not modified through the const interface, though it may be modified through other means. So, it just so happens that telling that an object is const provides good opportunities for optimization for the compiler, right. And for example, if an object is const and its address is not taken, then the compiler may not allocate any memory for that. It can just keep it in a read only table. Whereas, const expression's primary concern is to check what can be computed at compile time. So, making such computations type safe and usable in any compile time context. For example, size of an array, initializing enumerators, passing as a int template parameter, and so on and so forth. So, objects declare const expression have their initializer evaluated at the compile time. So, that is the basic difference between these two. Here is another example to show the concept. So, this is a const expression for variable declaration m. So, where const will also work actually. You can then define const expression C1 as m plus 1, which will be fine because m will be compile time 100. So, this is 101. But if you try to do, say, const expression int C2 of n plus 1, where n is a parameter, this will not compile, because it is not known to be a constant at the compile time. Whereas, you can do const on this, because all that it says, if you say const, is it says that when this gets executed at the runtime, it is not required at the compile time, but at the runtime when it gets executed, whatever is the value of n plus 1 will be the value with which you initialize C2, and that cannot be changed through this interface at least. Right. So, similar thing is for C3 being defined as C2 plus 1 and so on. Right. So, that is the difference between these two. Const expression is a very powerful mechanism to optimize at the compile time. The second feature that these features are all kind of diverse, because there are features on different aspects that are being talked of. So, there is a feature called no except to declare that a function will not throw an exception, or it cannot handle, it has not been written to handle exceptions thrown by functions within it. Right. So, we are saying that let us say extern C, a C function from the standard math library, we say that sqrt function is no except, which means that the sqrt function will never throw if I call it. It will execute and give me a proper value. So, using that I am defining some function for a my computation function for a vector, which I want to declare as no except. Right. So, what it says, this no except says that this function my computation either will not throw, or it is not written to handle exceptions to be thrown. For example, it is using sqrt these, so this will not throw, but it is also using say v size here, which might throw. But even if this throws, this function is not written equipped to handle that exception. So, that is the basic idea of no except. So, naturally that opens the question as to what happens if a function specified to be no except, if it throws. If it throws, then naturally you are violating the basic guarantee given by the code. So, this will in turn call a function in the standard library called std : terminate, which will terminate the function. Right? It is like, I mean, close to what abort does. You can also register your own function for terminate. Now, this function terminate does not do the typical tasks of exception handling. For example, it does not guarantee that the destructors of the objects that are getting out of context will be called. It does not guarantee that the stack will be properly unwinded, or it does not keep the provision of resuming the computation if the program has been found to have no further problem. So, you will recall that in exception also mechanism also we had a way to say no throw, no throw in this way. That is, it specifies what does a function throws, and giving an empty parameter says that it does not throw of any kind. So, which is semantically similar to no except, but the fact is this throws mechanism is actually runtime. So, it is far less efficient in terms of the exception specification, in contrast to what no except can do, which is a compile time feature being provided. Now, the interesting fact is many a times the no except can be used as a conditional, and that becomes particularly useful for templates. Right. So, what we want to say is suppose I have a function do f templatized by the type t, right, and that type could be kind of anything. So, what I want to say is this needs to use f v dot ati at I. At I is basically accessing a vector location, and so it is accessing the ith location of the vector and then using f. So, there are two function calls involved here. So, the guarantee that we want to say, we cannot say it is no except. If we give no except, then it is saying that it cannot handle anything. But what we want to say is this will be no except provided this expression, that is the call to at and call to f, they do not throw if they are no except. Right. So, it is kind of a conditional specification where, as you can see easily, that no except, instead of just being used as a qualifying keyword, it is being used kind of as a compile time operator. So, what does this operator do? It says that this will be true if f of v dot at 0 cannot throw. That is, if f as well as at are used as no except. So, it will check that, because I do not know for what f is, I do not know for that vector type what at might have been. So, this will give me a conditional. So, provided if this is no except, if this is true, then this becomes no except true. That means this function is no except, but if this is false, then this does not hold any good, right. So, the interesting factor about no except is it is a constant expression, that it is evaluated at the compile time. That is the reason I need at 0, and it does not evaluate its operand. It does not evaluate that, but it just checks the behavior, checks the specification of the corresponding functions and their no except status. So, no except declaration would typically be in the form of no except followed by an expression, and this will be true or false, and the plain no except is just a short form of no except true, right. Now, normally destructors should not throw, because then the cleanup becomes a mess. So, any destructor that you write, you should write it as no except. If the compiler provides the destructor, then it will be implicitly no except, provided all objects being destroyed in that destructor, the member variables are also have destructors which are no except, right. Similarly, the move operations must not throw, they should typically be no except. We will talk about the move expression very soon, but not in this module. So, no except is widely and systematically used in the standard library to improve performance and to clarify the requirements of where do you really need to do checks for the exception handling and where you can skip those. The next feature is a null pointer. You will wonder as to why do we need null pointer, we already had null pointer. So, this is a new keyword and a literal. Null PTR is a new keyword and a literal of a new type called new PTR underscore t, and this type is defined in std_def in C standard library. So, C std_def is where you will get it. So, this is a literal which is convertible to any pointer type and to bool, but nothing else. Now, if you look at the typical use of capital NULL as a null pointer, you will typically have a macro somewhere in std_def.h or cstd_def, which is defined as a 0. Right? So, that basically tells you that it is an integer 0 which is defined as a null. Now, some C, so this is what how C implements it, so which is compatible to C++. Some C compilers try to do something more intelligent, like specifying this as an integer expression, making sure that you get the proper integer type. Some write it as a void star null pointer and so on. Note that these are not compatible to C++. C++ typically will implement this as null 0, or in C++ 11 null will be defined as null PTR. So, what is the advantage of having this null PTR? It solves basically two problems. One is of function overload resolution and one is of forwarding templates. So, let us look at these through some examples. So, first let us have some examples of the null PTR. So, I have a integer pointer q initialized to null PTR, and the character pointer p initialized to null PTR, initialized to 0, initialized to null, p, p1, p2, all of these will work. Now, if I check p, it will compile, but obviously it will fail, because p is a null PTR. So, you can see that null PTR though is of null ptr underscore t type, it will get converted to bool for this if check. I can compare it with another pointer. P can be equated with P1, where P is initialized with null ptr and P1 is initialized with 0. So, this will compile and fail, this will compile as well as succeed, because both of them are actually null. But if I try to do compare q with P2, q is int star, P2 is char star, both are null, but their types are different, right. So, that conversion will not be allowed, conversion between distinct pointer types are not allowed. So, therefore, it will fail. Similarly, if you have a function g which takes a parameter of type int and you try to call it with null ptr, you will get an error, because as we said null ptr cannot be converted to int. If you try to initialize an int value with null ptr, you will also get an error. With capital null, both of these will actually work. Now, let us come to the function overload resolution. What is the problem? Suppose I have a function f with two overloads, one is int, another is int star. Now, often it becomes difficult to resolve a call for these overloads of the function. For example, if I write it say f0 in C++11, it will call the int version. If I write it as null ptr, it will get me the int star version, right, because 0 is a literal of int type. So, f0 is called to f int, null ptr is of type null ptr underscore t. So, f null ptr is a pointer type. So, it will be give me f int star. Now, if I had done f null, then which function would get called? The problem is that the compiler will say I am confused, because null is actually a value 0. So, considering null to be a value 0, this function should get called, but a value 0 can also be interpreted as a null void pointer. So, this value should get called, this function should get called. So, both of these overloads have equal weightage, and therefore, it cannot be resolved. So, using null, this kind of a function overload resolution was not possible, but with null pointer this will now be possible, because you are specifically saying that I want the pointer version. When you use 0, you specifically say that I want the integer version. This gets more involved in a forwarding template. So, let us consider what it talks about. We need a function h which takes an integer pointer. So, as you can easily understand, h0 and h null pointer both are okay. Now, I have a template of two type parameters f and p, and with that I templatize a function log and call, where f is actually a function parameter and p is a parameter to that function, right. So, it is kind of an application function which takes a function pointer, it takes a parameter and applies that function on the function parameter, right. So, it tries to make this call. So, it probably is doing some log entries and then it invokes this func on the parameter. Now, what will happen if you call this with h0? Now, with h0, the h is the func and the parameter is passed as 0. So, you want a template deduction to happen. By template deduction, this is int, right, 0 is int. So, it will be deduced as int and you are expecting a call to h int, which does not exist, h is int star. So, this fails. The same thing happens with null. If you pass it as null, then whatever is the type of hash defined null 0, maybe it is int, maybe it is defined as 0L, in which case it is long int. So, the compiler that I was using, the online GCC, as I talked of, it takes it as long int, the null. So, p is deduced as long int and h long int is searched, it does not exist and therefore, it fails. But if I call this with null pointer, null ptr, then correctly succeeds, because then param is deduced as null ptr underscore t type, and therefore, H is of this std colon colon null ptr t type that you are trying to call, and you have int star which we said can automatically convert. So, this function matches and the template will get forwarded easily, right. So, these are the two problems that null ptr, introduction of null ptr solves in terms of function overload resolution and in terms of forwarding template. The next that we talk of is inline namespaces, which is primarily for version management. Think about this is very simple. You have seen namespaces. So, the use case is a company is regularly releasing libraries of different versions. So, it had a version 98, say v98.h, and in that it defined a namespace v98 where the function is there. Now, what it has done, it is releasing the next version v99.h, and it has defined a namespace v99 where the function fint has been improved possibly, and another functionality f double has been introduced, and so on. The question is in the application code, how do you manage this? So, you have both of these, right. Now, what the company wants is, company wants you to move to v99 by default, but company also wants to give you the ability that if you want to stay with the older version, you should be able to make small changes in your code and be with that. So, how do you take care of that? That is very simply in mine.h, where you have included both these headers. You say you are using this mine namespace, and you say that if you want the old version, you say v98 colon colon f1. If you say the new version, then you say v99 colon colon f1, no surprise till. But if you just say f1, that is if you do not make any changes, then it defaults to v99. Why? Why does it default to v99? Because v99 is inline, right. So, that means that anything that is inline is available in the enclosing namespace. Enclosing namespace is global. So, these are available in the enclosing namespace unless you specifically use some other namespace, right. So, this default behavior is what is critical of the inline namespace feature. So, the company not only can provide the versions, but also is enforcing that if you are not consciously using the older version, then you will get automatically defaulted to the newer version. You can see the comparison of the inline namespace between C++03 and C++11. I have 3 nested namespaces with 3 variables, and I have to give complete qualification of these variables to be accessed properly. Whereas, if I inline the inner 2 namespaces, if I inline namespace ns3, then every symbol in ns3 is automatically available in the enclosing namespace ns2. If we inline ns2, all are available in ns1. So, actually using ns1, I can refer any of these variables implicitly. In addition, if I had done an inline of the outermost namespace, then the symbols would be available globally also, the feature that we are using in version control. The question would be, could we not have done this in C++03 we have using, right. So, here is a comparison of the C++03 namespaces, the same code as before on the left hand side, and here I have introduced 2 using, which give you the same effect. You can use everything from ns1, because using namespace ns3 as a part of ns2 says that anything in NS3 is available in NS2, and so similarly for here goes to NS1. Well, if I do that, then till up to this point things are comparable. Now, how do I make these available in global by default? What I will need to do is to put using namespace NS1. If I put using namespace NS1, then even simply writing V3 will mean this variable, because using everything is globally available. But that does not address the basic question, because this using namespace NS1 is in the code of the application. So, it is up to the choice of the user to put it or not put it, whereas when you do inline namespace, it is in the space of the library. So, it is a choice of the library designer. That is the subtle difference for which the inline namespace feature is very important for proper version control. The next feature is user defined literals, where the concern is very simple, that we say that user defined types, I mean in C++ we are building user defined types, but we cannot have literals of the types that we build. We can have only the literals of types that are already given. Some examples are given here. Even if I want to have take certain values and want to give them a specific meaning, say 123s, I want to mean that 123s is 123 seconds, I cannot do that. So, user defined literal does that by introducing a new literal operator, which is written in this form, that is operator keyword followed by a pair of double quotes, and then a suffix to be used with the literal conversion, right. So, in general this operator, so this is a computation. So, this operator will have this, then a suffix to actually, which is the name of the user defined literal operator, then it will have parameters of what you are converting from and the return type. The restrictions are that the suffix has to start with an underscore, otherwise non underscore names are reserved for the standard library, and parameters can be of certain types only, either an integer literal or a floating point literal or a string literal or a character literal, but the return type could be anything. You can take any of these and convert to a return type literal of your choice. So, let us see what it does. Say I define a string operator literal for the string. So, underscore s, all that I do is I just construct a string and pass on. I have a pointer to the character array. I need to pass the size, because otherwise I will not be able to do the conversion. So, if I do that and call this templatized function f with just the double quote, it is a pointed to character, right. It is an array of characters. So, it takes as const char reference size 6, 5 characters for hello and the terminator. But if I write it as underscore s, then it takes as a std : string object. It constructs an std : string object by calling this literal operator function. Similar thing can be done for say a complex. So, I am using an underscore I, the value is taken as long double, and I construct a complex object of the standard library. So, and then I use it like this. So, I am assuming that the real part is 0 and the imaginary part is provided by this literal conversion. So, this literal conversion 3 plus 4.0 I gives me a complex number 3.0 plus 3.0 4.0, because 4.0 underscore I literal gives me 0 4.0, then that is added to 3.00 and I get that. Conversions can be done with meaningful extension symbols like kg. I say okay, I have to deal with kilogram, gram, milligram. So, I have literals of every kind, and I will put a value and put the literal operator. So, the basic representation is in gram. For kilogram I multiply that value by 1000, for milligram I divide it by 1000. So, I say 3.6 underscore kg is my literal. So, that means 3600, because it will call this literal operator and convert. into grams, which is 3600 grams, and similar for milligrams and all those. So, this makes the code naturally lot more readable and understandable, and you can actually use this to convert to user defined types, like here run this example and check for yourself. I have defined a date type, date, month, year, and I want that this kind of a date literal I would have dd/yy/mm/yyyy and convert it directly to date object. This conversion function, the operator literal conversion function, allows me to do that. Just go through this carefully. It has a lot of parsing from the string. It takes it as a string, does a parsing, take out different parts, convert them into integer, and finally it constructs a data object as a literal. Okay. So, user defined literal is a very, very powerful mechanism. There are ways to either take the converted literal form or the raw string form in which it is provided. All of these examples are given here. Before I end, the last feature I would like to mention is raw string. You know that C strings have lot of escape characters, like \t is written to mean tab, \n is written to mean new line, and so on. C++ allows you to define a raw string which is written with a prefix capital R before the double quotes, which means that the escape characters will not be interpreted, they will not be treated as special. So, this will be \n \n, not to new line, right. Similarly, I can write a string like this which spreads over multiple lines. There are new lines inside, right. If you try to do this in a normal string, you will have error, but here you will be able to do that because everything is being taken just as the character is without any special interpretation being given to that. So, this becomes useful in some of the standard library features, as we will see later on. So, we have introduced a number of general features, these 6. So, please practice them through programming. Thank you very much for your attention, and we will meet in the next module.